All right, so what is this stuff about? Given a sequence AN, we maybe want to add these terms up. And just writing this formally, without thinking about it to begin with, we might want to add A1 plus A2 plus A3 plus A4, and so on. Forever, right? And if it's a finite sum, then we know well what that means. If it's an infinite sum, then we're going to have to think about what that means, because it's not obvious, right? It's not obvious we can make any sense of this. Yeah, but if we think a little bit about the things we know already, there are situations where we have already seen this, where it actually seems reasonable, even natural to us. So consider, let me just finish the sentence. This is called a series. And we need to give some meaning to this. But there are some situations where we see this already. So consider, for example, pi. Pi, as you know, is an irrational number, right? It is 3.14159 something something 5926 535, right? And the decimal expansion goes on forever. Yeah. But what is the meaning of this? What is this actually? Well, this is 3 plus 1 over 10 plus 4 over 100 plus 1 over 1000 plus 5 over 10,000 and so on, right? So the actual meaning of this decimal expansion is the sum of this infinite number of terms. Yeah, and you're all probably quite comfortable with this thing, with this concept of an irrational number. Well, the actual meaning of it is summing these infinite number of terms, and it does actually make sense. So we've been, or you have been, thinking about or considering series already, even though you might not have had it explicitly explained as being there. Okay, there's other simple situations where we another situation. If we take the number a half and then we add a quarter and so on, this is called someone's paradox, perhaps. But it's not a paradox. This thing makes sense. So consider quantity a half, right? And then we add a quarter. So this quantity right here is a quarter. And then we add an eighth. And then we add a 16th. From this picture, we can see what we're doing, right? We can see that every time we add half of the previous term, we are closing the gap between the sum of all of these terms and the number 1. By whatever gap is left, we close it by a half, right? And we can just see that if we keep doing this forever, then we're ultimately going to reach this point here, which is the point 1. You can just see it, right, from this picture. Yeah? Give me a thumbs up if that's making sense to you. Okay, so there are some examples of series where this thing, there are some examples where it is already a series, and say that better. We are familiar already with some things that are series where it seems to make sense to us, yeah? But we want to understand it in general. We want to understand it in general. And that is something we're going to need the concept of limit for. And it's going to proceed as follows. So we're going to start by considering just positive terms, but what I'm about to explain will work for positive and negative terms. But let's just start by considering positive terms. Yeah? So suppose we have A1, A2, A3 are all positive, bigger than or equal to 0. Then what is this quantity? We can think of this thing, the sum from I equals 1 to infinity, AI, as represented by this picture. Well, it is this picture. So we go from 0 to 1, and we put a block like this, whose height is A1. Right? And then from 1 to 2, we put a block like this. It might be higher, we don't know, whose height is A2. Yeah? And then from 2 to 3, a block whose height is A3. Like this. Yeah? And so on, right? We can do this forever, right? And then what is the meaning of this infinite sum? That is the same as the area of all of these guys added up going on to infinity, right? And so on. Well, maybe I'll just keep doing this, go off the edge of the board. This is A6, this is A7, and so on. So we would like to give some meaning to this, which corresponds to giving some meaning to the area of this infinite collection of blocks stacked up one next to the other along the positive real numbers. Yeah? That's what we'd like to do. Yeah? Cool. So, how can we give some meaning to this? Well, in general, without needing these A, K to be positive, we will form something called a partial sum. Which is defined as follows. We're going to call it Sn, and we're going to sum, usually from I equals 1, sometimes from I equals 0, from I equals 1 up to n, and we're going to add these guys. So that's just the sum, A1 plus A2 plus all the way up to An. That's the finite sum. Yeah? Are you all familiar with this notation here, this expression here? Yeah? Good. All this means is this. It's just a more efficient way to write this. And you should have seen this when we did Riemann sums. It should be comfortable for you. So this thing is a perfectly meaningful thing, right? It's a perfectly meaningful thing. Because we know how to add finitely many numbers, right? So on this picture, that corresponds to just taking a certain number of these blocks. Again, this picture is just for the case when we have positive elements, right? And stopping at some n. Yeah? But what we actually want is the entire thing, all of these guys from the first to the last. Yeah? Yeah? And what that should bring to mind to you, what this picture should recall for you is trying to understand the improper integral of type 1, where we integrate from 1 all the way to infinity. Sorry, when we integrate from 0 all the way to infinity. Yeah? It's kind of the same game, because we can certainly integrate from 1 up to any particular number, from 0 up to any particular number, but the improper integral of type 1 is the integral from 0 or whatever number all the way up to infinity. And we're able to do that by letting the right endpoint r go to infinity, and if there was a limit as r went to infinity, that thing was what we call the improper integral, because that thing was a meaningful answer as to what was the total area underneath the graph from 0 to infinity. Yeah? That's how we did this. That's how we discussed improper integrals. Yeah? And analogous to that, we're going to define the infinite sum, in other words, the series, in the following way. So we define the sum from I equals 1 up to infinity, ai, to be the limit as n goes to infinity of these partial sums. Yeah? So on this picture, that means we're taking more and more of these areas of these blocks, starting from the first one all the way up to the nth one. Yeah? And obviously, as we take more of them, then this number increases. Yeah? But if, as we do this, the limit exists, that thing is what we call the infinite series, the total sum of all of them. And it's completely analogous to what we did to define improper integrals of type 1. Yeah? And let me emphasize, we say we define because this literally has no meaning unless we do something like this. This is not just being fussy or being overly mathematical. This is literally a meaningless expression unless we define it in terms of a limit. There's no other way to do it. So here's a classic example. Consider this. Let an be minus 1 to the n. And then consider this series. I equals 1 to infinity ai. Yeah, what could that possibly be? Just the first two terms. So if we take S2, what happens when we add the first one and the second one? We get 0, right? If we have the first three terms, the first one, the second one, the third one, we're going to get minus 1. We have minus 1, 1, and then minus 1. So S3 is equal to minus 1. S4, the first four terms, it's going to be minus 1, 1, minus 1, 1. So it's going to be 0. And so on, right? So actually, we have that the Sn, when we have an even number, is just equal to 0, yeah? And when we have an odd number, which we're going to write like this, s to the 2k plus 1, that's how we can represent an odd number. It's always going to be minus 1, yeah? For k bigger than equal to 1. Yeah. So the partial sums will alternate between these two possible answers. It will alternate between either being 0 or minus 1 forever, right? So there's no way to give a meaning to this actual thing, the sum of minus 1 to the n. It's not that there is some number and we're just being fussy about what it actually is. It literally has no meaning. It's a meaningless expression. There is nothing we can. This thing there's nothing we can say about this because it just means nothing. So this thing means nothing, right? It is not either 0 or minus 1 or some kind of average of the two. It's literally meaningless, right? There's no meaning to this thing. It has no meaning. Yeah? So this is not about being super precise or fussy about things. There's literally no way to have a meaning of these infinite sums unless we define it through the process of taking finite sums and letting the number of terms go to infinity. And as we let the number of terms go to infinity, some consistent answer appears. And that consistent answer in the language maths is exactly saying that there exists a limit as n goes to infinity of the partial sums Sn. And if you think about it, that is all that we can reasonably say about this. That's the only, let me say that better. That's the only way we can reasonably make a definition out of this, right? I mean, we live in a finite world. We're alive for finitely many seconds, right? We're never going to be able to add something up infinitely many times. The only way we can know what this is if we add something up finitely many times, and we can prove that as the number of terms increases, the answer tends more and more consistently towards some particular number, which again, in the language of math, is exactly saying that the limit of the partial sums as n goes to infinity is equal to this thing. So there's no way to give meaning to this except as a limit. It's another instance where there's no way to proceed with this thing called calculus, unless we have the concept of a limit. Yeah, it's integral to this thing. Yeah? Okay, cool. So with this concept, we are indeed going to be able to calculate these series. And that's what this section is we're gonna talk about series quite a bit going forward. And we're going to start doing that by using this definition to try and calculate, to try and understand some simple series, and to try and understand when this thing makes no sense. So for sure, this makes no sense here, but we'll see there are other infinite collection of terms that we might like to add together that seem like we can add them together, but actually we can't. It's not going to work. The answer is not something finite. Okay? All right, I'm going to raise the board, and then we'll do some more of this. Example 1. Suppose we had a series where the Sn partial sum, the nth partial sum I equals 1 up to n of these terms, happens to be something that we can calculate, and it is equal to 2n over 3n plus 1. Okay? Suppose we have such a collection of numbers. Then this infinite sum, the sum from I equals 1 to infinity, an is equal to what? What is it equal to if we have this? The limit as n goes to infinity of these partial sums, right? And we are given in the question that these partial sums happen to be something we can sum to, and the answer is 2n over 3n plus 1. Yeah? So this thing is just the limit as n goes to infinity of 2n over 3n plus 1, and we're learning all about sequences and the limits, and we know, well, what this thing is, right? It's just 2 over 3. 2 over 3. All right, simple enough example. Second example, geometric series. This is one of the most important examples of series, and that's as follows. So that's when we have terms like this. We take the sum from I is equal to, in the most general form, I is equal to something. We start somewhere, m to infinity of r to, let me call it k, of r to the k. Okay, for some m. Okay. That's a geometric series. So the initial example, the second initial example I gave, which is when we had a half plus a quarter plus an eighth plus a 16th plus 1 over 32, that was a geometric series because it was just a half to the power of k, right? Example, i.e. the sum from k equals 1 to infinity, 1 over 2 to the k is 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 32, and so on. And that's the guy we discussed right at the beginning. And from the picture, we believe this thing is just equal to 1. Yeah? But it turns out that we can understand this in much more generality just by looking a little bit carefully at at this expression and its partial sum. So this is what we're going to do. So look at this. If we just start with k equals 0, so consider the simplest example, or consider the simplest formulation, the sum from k equals 0 to infinity of r to the k, okay? And we're going to take this partial sum, Sn, which is the sum from k is equal to 0 up to n of r to the k. Then we do the following little algebraic trick. Let's multiply r by s to the n. What happens? We multiply an r through this expression, right? And if we multiply an r through this expression, this is the sum from k equals 0 up to n of r to the k plus 1. Yeah? It's just, this is a finite sum. We're multiplying by r. We know what it means. Yeah? So, if we consider Sn minus r times Sn, what's this? Well, this guy Sn is 1 plus r squared all the way up to Rn, yeah? And then we're minusing this expression here, yeah? And the first term is r to the power 1, second term is r squared, and so on. The last term is r to the n plus 1. So minus r plus r squared, dot, dot, dot. And the last term here is when k equals n, so we have r to the n plus 1. Yeah? With me? And then we see this massive cancellation happen, right? We have this guy is killed by this guy is killed by this guy, right? We have a complete massacre. This guy is killed by the guy just before it, right? And the only thing that survives this are these two terms. It's just 1 minus r to the n plus 1. Yeah? Just a bit of algebra. But if we look at this expression here, we can factor this s to the n. So we have Sn 1 minus r, like this. Just factoring the Sn. But that gives us an explicit expression for what Sn is. So from star, Sn is equal to 1 over r to the n plus 1 over 1 minus r, like this. Yeah? Everybody with me? Okay, cool. And our job is to understand the limit of Sn as n goes to infinity, right? Yeah. So we need, or we want, the limit as n goes to infinity of Sn, right? And this limit has to exist for us to have some answer as to what this infinite sum right here is. So that's just the limit as n goes to infinity of this expression right here. 1 over r to the n plus 1 over 1 minus r. Okay, look at this. We've done this in the particular case when we have a half. Yeah? What situations, what values of r is this thing going to make sense for us? For what values of r do we have something meaningful here? Look at this. What is moving here? What is moving, right? We just have this n appearing right here, right? So we could rewrite this as the following. It's the limit as n goes to infinity. And let's break up this expression of 1 minus r, and then minus this thing r to the n plus 1 over 1 minus r. Yeah? We can do that, right? But if we do that, we see that this guy here isn't involving n, right? Yeah? So this is like a sequence whose every term is exactly the same. So we know this thing has a limit. Yeah? The limit of this sequence is just 1 over 1 minus r. So the issue is the limit of this thing. The issue is the limit of this thing. When is this thing here, which I put in red brackets, when is this thing going to have a limit? What values of r will make this thing make sense? Just pick some number and then consider what happens when you put that number into this expression. Yeah, a number between 0 and 1 would work. Tell me why. Because for any number between 0 and 1, that number to the power n gets closer and closer to 0. Yeah? Yeah, if we have 0.9 and we multiply it by itself over and over again, yeah, it gets smaller and smaller, it tends down to 0. Yeah? Yeah? Okay, cool. So for any number between 0 and 1, for sure, this thing vanishes, and then this limit will just be 1 over 1 minus r. Yeah? That stuff's okay. Yeah? That stuff makes sense. Cool. All right. Is that all the numbers for which this thing can make sense? Is that all the numbers for which this limit exists? What about 0? Well, it should indeed be fine, right? If we put 0 in, then this thing is just 0 no matter what. And this thing is just 1, so that should be fine. Indeed, if we look over here, if we have 1 plus 0, if we look over here, then when we have power of 0, we have 0 to 0 is 1, right? So then we just have 1 plus a whole bunch of zeros, so that will make sense. Any other values? Is that it? What about negative values? Are there any negative values that work? Yeah, why? Excellent, yeah. If we have some number which is between -1 and 0, strictly between -1 and 0, and we keep multiplying it by itself, yeah, then it's going to alternate between plus and minus, right? But it's going to get smaller all the time. This is something we also discussed when we talked about sequences, yeah? So for any number between -1 and 0, that works. So far, this makes sense. So this limit exists. For anything which is strictly bigger than -1, 0 is allowed, and strictly less than 1. Yeah? If we have 1, will this thing make sense? Yeah, from this expression we have infinity, right, which makes no sense. And if we look back at our original expression, we have r equals 1, then 1 to any power is 1, so we just keep adding 1 to 1 to 1 to 1 to 1, which is going to go off to infinity for sure, right? Yeah, so we have no limit as a number when we have r is equal to 1. What about r bigger than 1? Perfect, yeah, because r bigger than 1, this term is just blowing up, right? So it will not make sense then either. Yeah? Cool. What about r, which is strictly less than -1? Excellent. You guys are doing great. Yeah. For r, which is strictly less than -1, this guy here will just keep oscillating up and down further towards positive or negative infinity. Yeah, definitely won't converge. So the only values of r for which this thing makes sense, for which this limit exists, is this range. Yeah? And when we have this, then this limit is equal to, this is our original sum. Let me just rewrite it. The sum from k equals 0 to infinity to the k equals 1 over 1 minus r. That's what we've learned, right? That's what we've learned. Yeah? So we can explicitly find out what this geometric series is in this particular case. Yeah? Cool. All right, so I'm going to raise the board, and then we're going to use this to understand the more general expression. All of you who need to leave, please leave. I want to give a few more examples. Please watch them on the video afterwards. And I'll see everyone who leaves on Friday. Okay, so we know that if we take the sum from k equals 0 to infinity, r to the k, it's equal to 1 over 1 minus r. And again, way better that you work this out for yourself. Given the current chaos that we're in, you have a cheat sheet, you can put this on a formula, you can write this down. I need to memorize it. Nevertheless, going forward, you won't be able to do this. And for general understanding, much better you understand why, rather than just believe this is some kind of magical thing that you just memorize. So please do what I just did. It's a simple little algebraic calculation. All we did was we looked at Sn, so we just did this. This is all we did. We did Sn minus r times Sn. We found that this was equal to 1 minus r to the n plus 1. That's all we did. Yeah? And that's what gave this formula. So we know this, but we want to know we want to understand the sum from k is equal to whatever initial point I said m to infinity r to the k, right? Yeah. However, we can understand this by simply pulling out an r to the m from this entire expression, because the cool thing about series is when they converge, they behave just like sums. They are just as nice as sums, right? But let's do this carefully. So what is this thing? This is the limit as n goes to infinity of the finite sum from k equals m to n of r to the k, right? And then from this thing, we can pull out a power of r to the m, because our first power is r to the m. So I just write this out. First few terms, you see what I mean? This is r to the m plus r to the m plus 1, dot, 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 up to r to the n. Yeah? So we can factor out an r to the m from everything, right? Because n is the guy which we are taking to infinity, and m is just some fixed thing we have from the beginning. Yeah? So this is equal to r to the m, the sum from k is equal to m to n now of r to the k minus m. Yeah, just factor out a power r to the m, just some algebra. Yeah, oops, I need to write the limit signs. This is the limit as n goes to infinity of r to the m. Yeah. And this is the same as r to the m of this infinite sum. The sum. Now, if we start from k equals m, and then our term is k minus m, the first term will be r to the 0. The second term will be r to the 1. The third term will be r to the 2, right? So this expression here is the sum, is the same as, we write it like this, the limit as n goes to infinity. And now let's make the index equal from I equals 0 to infinity. So I is equal to 0 to infinity to the I. Yeah? Do you see what I mean? Yeah? Cool. So what is this? This is exactly the thing that we just worked out, right? This is equal to r to the m over 1 minus r. Yeah? Cool. So I did this quite carefully, but informally. If you see this expression, the sum from k equals m to infinity, r to the k, i.e. r to the m plus r to the m plus 1 plus blah, 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 blah. Yeah? Just factor out an r to the m. And then we have just the sum from k equals 0 to infinity, r to the k, which is just this thing, r to the m over 1 minus r. So I did this with the definition of the infinite sum being the limit of the partial sums because I haven't shown you that you can factor things out from an infinite series yet. So I did this step by step, but this is all we're doing. This is all we're doing. So we can do this formula for any general m. Yeah? Yeah. So our formula that we have was just when we started with k equals 0. So this is, in this particular instance, we're starting with k equals 0, and that's important. If we start with k equals 1, we get a different answer. If k equals 1, then we have r over 1 minus r. Yeah. This is another reason not to memorize the formula, because it looks almost exactly the same. Almost the most general thing. In the most generality, we can have some expression like this. We can have an expression from the sum m is equal to, k is equal to m to infinity. Some number, let's call it a, and then r to the k. Yeah? And then this turns out to be just a r to the m over 1 minus r, for exactly the same reason that we can just factor out the a. We can pull out the a from the limit for exactly the same reasons like this. Now, this infinite sum is just the limit of partial sums, and the partial sums we can factor things out, because partial sums are just finite sums, we know what we're doing with them, and this becomes this. So informally, just pull out the a from this expression and use the previous one. Okay? All right, so in the book, it starts with this thing. And I don't want you to do that. I want you to build it up from the simplest expression, which is this thing. So make sure you understand this thing by doing it yourself, by working it out from this little argument. This is one line. This is one line. This is not hard. Yeah? So work it out from this one line so that you know for sure, you're absolutely certain that this thing is this. Not believing anybody, you've worked it out, you know for sure. Yeah? You have a solid foundation. Then work out what the sum is when we start from m. And it just is equal to this thing because we just factor out an r to the m. That's easy too. Then we have the most general expression, we just factor out an a, and that's the general answer. That's what you want. Okay? All right. Once you're solid with these things, then it's hard to mess up then. Let's do an example. Example 3. Find the following. 5 minus 10 over 3 plus 20 over 9 minus 40 over 27, and so on. Okay, so solution. Obviously, this is going to be a geometric series because it's just coming off of this explanation. It doesn't look like one yet. Yeah? So let's try and make the most obvious simplification. It would be nicer to start with 1 because that's the general expression we have when we do from k equals 0 to infinity. So let's factor out a 5 from this thing. So if we factor out a 5, then we're going to have a 1 minus 2 over 3 plus 4 over 9 minus 8 over 27, and then so on. Huh? And now that looks better, right? That looks better. That looks more like a geometric series. Yeah? At least the stuff in the brackets does. Yeah? So what is this geometric series? This is equal to the sum from k is equal to 0 to infinity of what number to the power k? Negative 2 over 3, right? Because if we take negative 2 over 3 to the power k, then for k equals 0, we have 1. For k equals 1, we have this expression. For k equals 2, we have this expression. K equals 3, we have this expression. Yeah? You will see it. Give me a thumbs up if you're with me. And then we know what to do. This expression is just our most classic form of the geometric series. It's 5, and then it's 1 over 1 minus r. And r is minus 2 over 3. So it's 1 minus minus 2 over 3. So it's 1 plus 2 over 3. Yeah? Which is equal to 5. Let's write it in this form. Let's write this guy as 3 over 3 plus 2 over 3. So it's going to be 5 over 3. Yeah? And that thing is just 3. Yeah? Easy. Easy. So when you're confident about what these geometric series actually sum to, then this thing is not hard. Let's do another example. What about this? Let's do this. This will be our final example. Example 4. Does the sum from n equals 1 to infinity, 2 to the 2n, 3 to the 1 minus n converge? Look at this. I think you sound like you have exactly the right idea, but let's use the language of maths and express your idea with that. So the point is that 2 to the 2n is what? What do we understand this to be? 4 to the n, right? Yeah. So when we look at this thing, 2 to the 2n over, let's write this guy as 3 to the n minus 1, which is the same as 1, which is the same as 3 to the 1 minus n. If you write underneath, it's 3 to the n minus 1. Yeah. then what is this? Then this is the same as just 3 times 4 to the n over 3 to the n. Yeah? Which is the same as just 3 times 4 over 3 to the n. Let me put that underneath. So instead. Which is the same as 3 times 4 to the 3 over n. Yeah? Yeah? And these terms, you know, are blowing up, right? So this is like this series here, let's call it star. So star is like the sum from k equals 1 to infinity of 3 times 4 over 3 to the n. Yeah? We can pull out the 3. Well, let's not do that. Let's just leave it like this. And if we look at this, then this number r is bigger than 1. Yeah? And we don't believe it's going to converge. In fact, if we just look at this number 4 over 3 to the n, it gets bigger and bigger and bigger. So if you visualize what this is meaning, it means that when we put a bunch of blocks like this, then each block is bigger than the last one, right? Yeah? Yeah, if we add infinitely many of these terms. So for sure, the total area underneath all of these blocks is never going to be finite. Yeah? Do you see what I mean? So our general rule, a general fact that this thing is only going to make sense if r is between -1 and 1 tells us that this thing is not going to make sense, it's not going to converge. And if we just think about what this looks like, it looks like this. Of course, it's not going to converge. Yeah? Cool. All right. So that's our last example for today. We will continue talking about this on Friday. I have office hour now. Stick around if you have any questions. See you all on Friday.